So for this project, we decided to build a antenna, and we worked on an antenna. So why antennas are useful? So antennas are virtually the interface between radio waves and electric currents, and they are required by any radio receiver or transmitter to couple its electrical connection to its electromagnetic field, and they're used by anyone that has to use high-frequency communication, such as the telecommunications industry, for ultramassive MIMO, for 6G communication systems, or Earth orbiting satellite ground stations, and many other users. So for this specific antenna, we wanted to design it to receive the ITU frequency band of 2200 to 2290 with a frequency operation of 2250 megahertz with a bandwidth of at least 90 megahertz with no grating lobes, and we wanted so that we could receive the Jason-3 satellite. And Jason-3 satellites are very useful altimetry science mission that allows understanding of better science models for forecasting different. Right, so the antenna was designed with a frequency of operation of 2.2 gigahertz around there, so pick up Jason-3, and then also having a bandwidth of at least 90 megahertz, and avoiding grating lobes by ensuring element spacing of half a wavelength. So yes, so how have we done this? So yes, the epsilon R used in simulation is 4.3, the substrate height is 1.6, and the metal thickness is 0.35, so we have metal on the bottom and we have a metal on the top for the patch, and then metal for the ground plane, so to act as a reference plane for all the signals. Regarding the substrates, so the substrates is FR4 4.3, and so we can check the impedance. So for the S11 measurement, we have a at the Jason-3 frequency of 2.15 or 2.21. We have an S11 of minus 12, which indicates that less than 10% of your signal is actually being reflected, which is very good. And it also has a good impedance bandwidth, so it goes from 2.16 to 2.3, or a bit over, so at least like 140 megahertz of impedance bandwidth according to the simulations. And then regarding the actual far field plots, you have a gain of 5.53, and you have a angular width of 27.4. So yeah, this concludes the simulation.
The following antenna manufactured and fabricated. So a SMA edge connector was attached to the edge of the SMA microstrip trace, and the signal trace was then soldered directly onto the PCB, and then the ground pins were soldered onto the bottom of the antenna. So from the measured signal, it seems like the S11 and the antenna is resonant on matching on 2.155, which is not the frequency that was designed on, which was 2.215. So this would likely indicate that there would be a difference in the dielectric constant. So probably the dielectric constant would be higher than the one that was used in simulation. To perform the 3 antenna test, the antennas must meet the Rayleigh criterion of the far field, which means that the antennas must be spaced, in this situation, at least 80 centimeters away from each other. Second is that the antennas must be aligned bore side to each other, and then there must be also negligible proximity and multipath interference between the 2 antennas. And then now, to calculate the gains of the antennas, each S21 measurements must be performed simultaneous, in 3 different system of equations. So first of all, you would calculate the S21 at the antenna here. Then what you do is you switch out the antenna with this one, for instance. You switch out that antenna there, and then you would then measure S21 again, and then you'd perform that same procedure, switching out, well, probably this antenna for that antenna, and then leaving this antenna here, and then solving those through, using those 3 S21 measurements, you can then plug them into a system of equations and then calculate the gain. And then that's how you perform the 3 antenna test.
So the main difference between the measured and the simulation was that the frequency of operation that was noted was that the frequency was 2.153 gigahertz, and this is quite different from the 2.215 gigahertz that was actually measured in made in simulation. Why is this? It's because likely the dielectric constant that was used is different from the used in simulation. 4.3 was different from the dielectric constant used in measured. So dielectric constant seems to be 4.8. Why is there such a difference of dielectric constant? Well, it's because FR4 is a different dielectric constant depending on its resonant to glass weave pattern, making it inhomogeneous and giving different dielectric constant values across frequency ranges with different manufacturers such as JLC, PCB, and PCBWay. So if you're using for high precision radio frequency and microwave applications, to ensure that you have a homogeneous and predictable dielectric constant, it would be advisable to use a homogeneous substrate like Rogers for the microstrip patch antenna ring. So future work would be needed to correct for the dielectric constant.